Let's have a brief introduction to the continuity of a function of one variable at a point. So what does it mean for f of x to be continuous at x equals a? So if I make that statement, f of x is continuous at x equals a, what does that tell us? Well, intuitively, or like sort of a basic feel for it, it means this, that when we get to x equals a, that if we were going to trace over this red function with our pen, that when we got to x equals a, we wouldn't have to lift our pen at all. We could just keep tracing right through and it'd be no problem. If we were walking along this function, it'd be no problem. We wouldn't see any breaks in the path or in the road or anything like that. But how do we define that mathematically? Well, we can use the idea of limits and functions. So this function is denoted as f of x, and here's what we know. As we approach a from the left side, we're approaching a particular y value. Whatever this y value is, we'll call it L. And we approach a from the right side, we notice all these y values here are also very close to L. And then lastly, at x equals a exactly, the y value is exactly L. So we can write that as one mathematical statement. We can say that the limit as x approaches a from the left of our function is equal to the limit as x approaches a from the right of our function. And both of those things are equal to the y value when x is exactly a. So we say a function is continuous at x equals a if this statement holds. Now, if you were to go out there reading and looking at other what seem to be different definitions of continuity, they're really all the same. Here's another one. It's sort of like a checklist. You have to check three things. So they say a function is continuous at x equals a if f of a exists. Well, that's just sort of like a prerequisite. If you didn't have a y value when x equals a, then how could the function be continuous there? The limit as x goes to a of f of x exists. Well, if you think about it, that's what these two statements are saying. If I'm insisting that the limit from the left and the limit from the right are the same, then the limit's going to exist. And then lastly, the limit as x goes to a of our function has to equal the y value when x equals a. And that's sort of what this last part was all about. So that's sometimes another way you might see the definition for continuity of a function at x equals a. All right, so what are the ways a function can fail to be continuous? Well, there's a couple of famous examples. The first of which I'm going to call a pod, which stands for point of discontinuity. But basically, here's what the function does. It comes along, it's got a hollow dot in it, and then it continues. So this function f of x is continuous everywhere except when you get to this number a. And if you think about it, the limit as x goes to a from the left of this function is right there. And on the right, you have the same limit. So the limit's equal, the limits are defined, but it doesn't equal f of a, and that's because f of a does not exist, at least the way I've drawn it here. Okay? Here's another way that can happen. You can have something that looks like a pod, but the function comes along, hollow dot, and then continues. So clearly, the first two limits over here work. This limit equals that limit in this case. But maybe at x equals a, there's a solid dot up above it somewhere. So what changes is the last thing. We would say this doesn't equal what f of a equals. And if you think about it, if you tried to trace over either one of these graphs, I'd be coming along, I had to lift my pen and then continue. I'd be coming along, I have to lift my pen up, fill in this dot, and come back down and continue. So that's one of the first ways a function can fail to be continuous. Another way is something like this. It's called a jump discontinuity, or just a jump. Graph comes along, hollow dot, maybe it's solid here, and then continues. And what happens in this case is that when you compare the limits from the left and right, they're not equal. So you don't even need to consider what's happening with the y value at x equals a, because the limits didn't even match. Y values on the left of this number a and the y values on the right of the number a are not the same. Okay, and then a third, one of the most popular ways to see a function fail to be continuous is VA, or a vertical asymptote. So if you consider a function that does something like this, here we go, it's coming along. Maybe it shoots up like this. Maybe it shoots up like this on the right. The limits on the left and right both equal infinity. But in this case, f of a does not exist. So there'd be no way to trace over this without having to lift your pen. Okay? If you think about where vertical asymptotes come from, we shouldn't really be surprised. They come from where a denominator of a rational expression doesn't equal 0. So that's a brief introduction to when functions are continuous and not continuous. Thanks for watching.